All right, let's talk about this key for determining molecular geometry practice. To do this, you should go to this website. It's the one that is made by PhET, and it'll give you a good way to view all of these. Okay, so what you need to do is draw the Lewis structure for each of these molecules, determine the number of regions of electron density, so how many sides of the central atom are taken up by electrons. That'll give you the name of the electron domain geometry, and then determine the number of bonding regions, so how many sides are used to make bonds, and that will give you the molecular geometry. Okay, these two things here are given to you in the simulation itself down in the bottom left corner. So let's go through this. The first one is done for you, and let's move on to CH4. So CH4 would have a Lewis structure that looks like this. Again, you can use the lines or two dots. It has four regions of electron density, meaning it's tetrahedral, and all four are bonding regions. So the molecular geometry is also tetrahedral. Again, if you have that handout that I gave you, the little chart that I told you not to lose, that would be very helpful in doing this. Silicon tetrafluoride would have this Lewis structure. All four sides have electrons around it, so it's tetrahedral. And the four sides are all bonds, so it's tetrahedral as well. Okay, let's go down here. CHCl3 will have this Lewis structure. All four sides have electrons around it, so it makes it tetrahedral. And all four sides are bonds, so its molecular geometry is also tetrahedral. The last one on this page is the nitrate ion, NO3 minus. So you have to add one electron to the overall structure to get it to work, and you designate it with brackets and this negative sign up in the top right corner. Remember, this double bond could be here, here, or here. It has three resonance structures. The regions of electron density is only three because there are only three sides used around nitrogen to show electrons. That makes its electron domain geometry trigonal planar, and the number of bonding regions is 3, of course. That makes it trigonal planar. Okay, let's move on to the next page. What we have here in CO2 is two double bonds around carbon. That means that there's two regions of electron density, which makes it linear, and the molecular geometry thus is linear as well. We have here in PCl3, phosphorus trichloride, four regions of electron density, 1, 2, 3, 4. That makes it tetrahedral, and its molecular geometry is trigonal pyramidal because only three of those sides are used to make bonds. Okay, and there's one lone pair. Going down here, hydrogen cyanide, HCN, has a single covalent bond for HC because hydrogen can only have the two electrons, and then there's a triple bond between carbon and nitrogen with a lone pair on nitrogen. That makes this linear because around the central atom there's only two regions where electrons exist, and it would have to be linear as well in its molecular geometry. All right, let's move on to this one. SO2, sulfur dioxide, it would have a resonance structure in addition to this one where the double bond is over here. You can see that there's three regions of electron density, one of which is a lone pair, so that makes the regions of electron density trigonal planar, but this is a bent molecule because it has a double bond, a single bond, and one lone pair. Okay, and you can verify that with the simulation or looking at the chart that I gave you. Now moving on to water. This one, as you probably know, is also bent, but it has a tetrahedral electron domain geometry because it has 2 lone pairs and 2 bonds. So 4 sides are used, making it tetrahedral, but only 2 of them are used for bonds for the hydrogens, and that makes it bent. And then the last one is ozone. This one I did show the resonance structure because I had some space. So the double bond could be on the right side or on the left side. Either one works. And there is a lone pair on the central oxygen. That makes 3 sides used by electrons. That's the regions of electron density, making it trigonal planar. But because this molecule only has 2 sides that are being used for bonds, it's very similar to SO2. And I hope you see that both of these are bent because having 3 oxygens is similar to having 2 oxygens and a sulfur. All of these are in the same group. So they all act very similarly, and you'll expect them to have the same shape. Okay? So let me know if you have any questions about this. I'm happy to help. Thanks for watching.